So the first trend deals with size. Now the easiest one, as we move further down a family, the radius gets larger, the atoms get bigger. Now we could rationalize this a number of different ways, but probably the easiest way to rationalize it has to do with the electrons. We have our shells, n is equal to 1, 2, and 3, and one of the artifacts of this electronic structure discussion that we had last week is that the average distance away from the nucleus increases as you increase your principal quantum number. And every time we move down a period in the periodic table, down a column in the periodic table, and we increase our number of electrons, and we increase the principal quantum number, n. So basically we're getting a bigger shell. We're moving out further away. The electrons on the periphery are further away from the electrons in the core. Now, you can see that represented here, and again, these are radii. This would represent a lithium ion going down to sodium, and it's a quite regular increase. Going down a different column, you can see that this also increases. So in general, the deeper you are in the periodic table, the bigger the atom. So within the same column, so within the same family, going down the periodic table, the size increases. And again, we can rationalize that pretty simply with the distance away from the electrons on the periphery. And every time you create a new shell, those electrons get further away. That's going down the periodic table. Going across the periodic table, it's a little harder to rationalize. They are also increasing in the number of electrons, but going across the periodic table, we see a slightly different trend. Notice, going across the periodic table, for all intent and purposes, the atoms are getting smaller and small. And there are deviations. Notice how nitrogen is a little bit larger than carbon. But they increase and decrease, decrease. So going down the periodic, across the periodic table, the size actually decreases. Now this, at first glance, doesn't seem to make sense. We're adding more electrons. The electrons should be moving further and further away. But they're all going into the same shell. So if you take a look at oxygen, if we just look at the valence shell, 2s2, 2p4. The valence shell has these electrons in it. The rationale for this is we have to introduce a new concept. If you go back and listen to some of the other lectures, I hammered on one point over and over and over again, and it dealt with s orbitals. All right? It turns out that the s orbital has density at the nucleus. So s orbitals are interacting with the nucleus. The electron has some residual density at the nucleus. And so what that means is that the s electrons interact a little more strongly. And so this is one of the reasons why the s orbitals are lower than the p orbitals within the same subshell. Within the same shell, the s's are a little bit more stabilizers than the p's because of this stabilizing force, the fact that they're interacting with the nucleus. Additionally, electrons at the nucleus, you can think of them as acting as a barrier. So you have this nucleus, which is a positive charge, and then you have these core electrons that sit between the nucleus and the valence electrons. So these valence electrons in the outside, and so in this helium's case, in this oxygen's case, you have these 6 valence electrons on the outside, and then this helium acting as sort of a helium core but it's not really the helium core, it's the helium electrons in the core acting to mute the external electrons. The nucleus is attracting the electrons. That's why the electrons are there. They're attracted to the nucleus. These outermost electrons, though, are kind of being repelled by the electrons on the core. But as you go across the periodic table, you are increasing the charge in the nucleus. If we just look at the outermost, if we take a look at lithium, we see that lithium is atomic number 3. Lithium is atomic number 3, beryllium is atomic number 4, boron is atomic number 5, carbon is atomic number 6, 7, 8, 9, 10. These are positive charges, and so what you're doing is you're sequentially increasing the positive charge in the nucleus. And by increasing the positive charge in the nucleus, you're creating more attractive force between the electrons. And so here we have this argon core, this helium core, in this case the helium core, which consists of 2 electrons. And so these 2 electrons kind of mute 2 of the electrons, 2 of the protons, but we still have 3, 4, 5, 6, 7, 8, 9 protons attracting these outermost electrons. And so you end up with a compression. The electrons get compressed. They are attracted to the protons. And so as you increase the nuclear charge, the atoms get more and more compressed. So going across the periodic table, the nuclear charge is increasing, but the distance that the electrons reside in doesn't. And so you're cramming more and more charge into a smaller and smaller area, increasing the attraction for those electrons. Now, this shielding by the helium leads, we're not really measuring nuclear charge, we're measuring effective nuclear charge, the effective charge that the outermost electrons feel. So nuclear charge or effective nuclear charge plays a role, and we see that going across the periodic table. What that means is we can actually get some strange size effects. The rubidium atom within the same period is much, much larger than the corresponding xenon. Now we have to be careful making assessments when you say something like xenon and potassium, which one is larger, but for the most part, 2 elements that are close on the periodic table, the one closer to the noble gas will have the smaller size. And so we can predict which one is larger or smaller based upon its location on the periodic table. Now, what about ions? Now, ions show a similar trend to what we just discussed, and we can rationalize their behavior the same way. So let's take a look at a number of ions. Lithium, 1s2, 2s1, versus beryllium. Now, for the cations, when we ionize these compounds, what we're often doing is stripping out the outermost electrons. Now, this does 2 things. When we strip out those outermost electrons to form lithium plus with its 1s2 configuration and beryllium plus 2 with its 1s2 configuration, where we've lost those outermost electrons, we are effectively stripping it down to the next shell compared to the cation, the unionized material. So we are moving down in the shell, making the cations much smaller. So a cation is generally smaller than its respective neutral atom. Additionally, we're increasing the charge relative to the size of the atom, making its effective nuclear charge much higher. And so this additionally compresses the ion. So the smallest ions will have the highest charges because they have their shells stripped away. Additionally, as you go deeper in the periodic table, the ions get bigger, So we still have to take into the relative size effects. In general, within a family, the smaller the atom, the smaller the ion. So that's usually going to trump. But going across the periodic table, it's not the same. Now, anions, something like fluorine, 1s2, 2s2, 2p5, when it ionizes to form F-, 1s2, 2s2, 2p6, it has gained an electron. It has gained an electron. And by gaining an electron, it alters its effective nuclear charge. There are 9 electrons in fluorine balancing out 9 protons, whereas now you have an extra electron. It is not as attracted, because here we have an effective nuclear charge of 9 versus an electron count of 10. Meaning those 10 electrons start to repel one another and sort of drift a little bit further, and forcing these ions these materials to sort of swell. So in general, the anions of an element will be significantly larger than the neutral compound of the same element. Again, this again stems from electronic structure. So understanding the electronic structure of the ions helps rationalize why these ions are bigger. Now, if we have isoelectronic series, an isoelectronic compound series, isoelectronic means same number of electrons. So if we have something like O minus 2, F minus 2, F minus 1, neon, sodium plus, and magnesium plus 2. In these cases, they all have the same number of electrons, 10. The one with the lowest number of protons, in this case oxygen, will be the largest. And so within this series, they get smaller going across the because of the effective nucleus charge issues. Again, this one has Z effective of around 6 or 7, and this one has Z effect of about 12. Right? And so increasing, or 11, increasing the number of electrons, 12, yeah, protons compared to the number of electrons. Those 10 electrons around the magnesium are attracted and compressed. So be prepared to make these rationales if you're doing assignments based upon relative charge, not size.